Specialist Solutions Engineer inside the virtual networking team at VMware. I'm focused on all things SDN, whether it's the data center or the WAN. Today we're going to be focused on networking and security automation with NSX-T. NSX-T has been around for a while now, but its key focus and use cases are around providing security for microsegmentation and east-west security enforcement across the data center. NSX-T, though, is also a cloud-native solution. We can talk to existing cloud providers directly through their APIs and provide a coordinated approach to security and network creation of both across existing on-prem solutions as well as into public cloud infrastructure. The solution is therefore inherently a multi-cloud solution that allows you to build security constructs that follow workloads regardless of which compute platform or hypervisor they are using, as well as logical networking constructs to connect them together. Today we're going to be focused on the automation use cases around logical network creation and security enforcement. So host virtualization inside vSphere has been our bread and butter since day one. It's allowed the operators to deploy virtual machines on top of existing compute workloads and deploy multiple virtual machines onto a single x86 host. I don't think we want to go back to the days of deploying individual bare metal hosts for every single workload. And we have to ask ourselves why the networking infrastructure teams are still running with multiple physical appliances for routing and for security and higher layer services as well, and we can just virtualize those. So the goal of NSX-T is to virtualize everything that sits around the compute infrastructure. The first challenge we face inside the data center is once we've virtualized our workloads, we can move virtual machines around, which is fantastic. But when the operator starts moving a virtual machine across a layer 3 boundary, things quickly come undone. Our layer 2 construct inside the VDS is not able to actually communicate across the layer 3 boundary. So the underlying network infrastructure team is therefore tasked with the ability or the requirement to provide layer 2 over layer 3 networks. This can be achieved through several means from different networking vendors, but this is driving complexity into the underlying networking infrastructure and driving dependence on technologies and platforms that deliver those services for the network. It also drives a lot of complexity in troubleshooting and long lead times to resolution when there's an issue. So once we provide this connectivity across the network, then virtual machines can be free to move around the network, between racks, between data centers, or across the country. So any solution we're looking at delivering with NSX-T around network virtualization also needs to take this into account as well. How do we address the layer 2 over layer 3 problem that has been delivered by the networking teams historically? The next challenge focuses around security. Businesses are increasingly be driven to secure workloads. In this case, we have a challenge here to secure traffic from VM1 to VM2. So the network operators and the security team would deploy a centralized firewall, and all traffic would have to pass through this firewall to pass security policy. This challenge is further increased when we exceed the limits of those firewalls, whether we're exceeding the bandwidth on the interfaces we're provided or we've blown out the session capability of a firewall. The challenge is then we deploy another firewall and provide another configuration touch point to the network and another piece of hardware to integrate into the network as well. So again, we need to address this with any network virtualization solution that we're positioning here as well with NSX-T inside the data center. So once we get these products deployed inside the network and we get security enforcement occurring, we often see hairpinning of traffic through a centralized firewall model as well. This can lead to inefficiencies inside the network infrastructure. We could be forwarding packets across the network to the firewall, which ultimately are just being dropped by the security policy. And this is driving inefficient use of networking hardware and the links that are connecting the data centers or the racks together. So again, let's address that inside NSX-T as well and provide a security model which removes this challenge and the burden of ever-increasing security appliances inside the data center. So how do we address this with NSX-T? We have an overlay model. There is a new type of interface that appears inside the VDS on an NSX-enabled hypervisor host, which is known as a TEP interface, the Tunnel Endpoint Interface. These are layer 3 interfaces that forward IP packets between them, and This TEP interface and the VDS is now responsible for encapsulating a layer 2 frame from our virtual machine, in this case VM1 talking to VM2, and wrapping that up into a tunnel from end to end. So the challenge we had in the underlying network infrastructure to deliver layer 2 frames over an IP network has now been pushed into the kernel itself directly and addressed by the tunnel endpoint interface. So we're taking away the requirements and the complexity that was pushed onto the network to actually achieve this for us in the first place. And we're doing this through a completely software-based construct inside the hypervisor itself. So if the operator now decides to move a virtual machine across the network, the centralized NSX-T controller is responsible to update the tunnel endpoint information. Virtual machine now is moved from A3 to B3, so the destination IP address of the tunnel has also changed as well. And the underlying network infrastructure, the switches and the routers, are not aware of this taking place. All they are aware of is that I'm now getting packets destined for a remote IP address which I'm routing towards. And as we know, all modern networking infrastructure and equipment is capable of forwarding IP packets for us. So the underlying network is no longer required to do anything more than simply forward IP packets and provide IP connectivity end-to-end across the network, which every existing switch and router deployed inside a data center can achieve today. And obviously anything you're looking to deploy can do that as well. So we're removing the requirements for the underlying network infrastructure to be delivered by any single vendor or be tied to any specific life cycle of those products, because at the end of the day, the common denominator is that they have to be able to forward IP packets for us across the network. Right, so this allows us now to logically instantiate multiple networks and multiple tenancies across our network infrastructure as well. If we're pushing all those requirements into the kernel, we can simply ask it to build multiple logical routers inside the kernel and connect those together through the same common tunnel infrastructure. So in this case, I have 3 tenancies. I've got a blue, an orange, and a purple network, which all share the same networking infrastructure. But through our VDS, we are now completely isolating all these virtual machines from each other, and allows us to build security policy and enforce a security posture directly onto the kernel, and enforcing security policy prior to transmission onto the physical networking infrastructure. And we do this through inserting a logical firewall directly onto the VNIC inside the VDS. So every single virtual machine across the network, whether it's a legacy VM or if it's a container pod attached to the VDS, has the same firewalling capabilities. So it's a stateful firewall, but we also support up to a full layer 7 packet inspection as well, and a fully distributed fashion, which is considered configured through a central management interface. So this distributed firewall capability, which is baked into our product, obviously we have local switching capability that the VDS has always had, but each tenancy across this network now has complete visibility to the entire routing table for its domain. We have integrated load balancing capabilities, whether that's the basic load balancer built into NSX-T or the advanced load balancer provided through integration with RV networks. And just like a physical firewall, there's other services that those platforms provide as well. So things like IPsec termination, we move that into the NSX-T fabric as well and provide that as a native solution into this product and remove dependencies on those centralized firewalls to provide those capabilities for us. We need to add IPS into the slide deck as well, because IDS and IPS are now available inside NSX-T, allowing you to inspect every single packet out of every single workload. So not just having micro-segmentation for a stateful firewall, but having micro-segmentation right down to a distributed IPS solution across the network. And a centralized IPS product is typically constrained around the amount of throughput it can handle, and it's a very taxing task to push onto an IPS product. And this leads to compromises being made in the security posture and which workloads, which tiers, which applications are being protected by IPS. If we pass every single packet through a distributed IPS system, then we can deploy IPS en masse at scale across the network. And every compute node that we add to the network simply just increases the scale of our distributed firewall and distributed IPS solution at that point. Now, firewalls and routing platforms in the network also provide other services, so source and destination NAT services, address translation, but DHCP relay and DHCP services integrated into the platform. These two are also built into the fabric as well. So we're removing dependencies on these types of services and capabilities from the network itself, and just really pushing simplification into the network that all it has to do is forward IP packets for us. So network automation And network virtualization is where any modern enterprise is taking their data center infrastructure. Network automation is really looking to replicate the life cycle and the operations that a human network operator would make. They would log into the physical networking switches and configure VLANs, and configure routing, configure ACLs and the like, and log into firewalls, into load balancers, and really stitch these entire things together. Network automation is simply taking the same approach, whether it's through CLI integration or through APIs onto individual boxes, and making the same changes, but doing it through an automated process. We still have dependencies at this stage on which vendors are supported by these products, what operating systems they support, what versions of those operating support as well. So you're really just taking what is a broken process and automating it in a faster fashion. You still have the same challenges at the end of the day. Network virtualization, on the other hand, is looking to logically instantiate an entire network based on the topology and the design you wish, and deploying that onto the network and stitching it together using overlay tunnels to provide that backplane connectivity between them. And because the packets on the overlay are simply using IP, the underlying network fabric can be from any vendor, any device, any topology. Your existing legacy network environment inside the data center or your new IP fabric you're building are all equally supported. All those higher level services are pushed directly into the VDS and the distributed firewall, and this runs across your existing infrastructure, between data centers, between racks across the country. So the day in the life of a networking engineer is to take the requirements of the design of a network and then instantiate that across the network. So traditionally they would log into physical devices and they would configure these elements. They're responsible for tracking the use of VLANs and subnets that are allocated and which interfaces have been configured. And importantly, when these things change as well, they have to keep up to date with that. So come through and actually remove entries from the network, update an interface, free up a VLAN or a subnet. So there's a lot of manual labor in actually tracking half of these things. There's many moving parts. It can be difficult to troubleshoot, and especially if it's not documented well as well. It's slow, it's error prone. Is there any wonder that the networking guys get the fingers pointed at them when things aren't happening as quickly as the virtualization team would like? And before you jump up and down, I'm a networking engineer, and I've had that finger pointed at me many times. With a software overlay approach, we're allowing the network operator to logically design what the network should look like and have that reside on top of an existing IP network. And because we're simply forwarding IP packets across this network, we're not logging into switches to make changes. We're not logging into a router to reconfigure anything. The network, the underlying network infrastructure is inherently low touch. So no one ever has to log into those devices ever again effectively in this type of solution. So it lets a user build and destroy an overlay network on demand within seconds. And the system is keeping track of all the utilization, all the allocation of addresses and resources across the entire network for you. And through tight integration with orchestration platforms like vCenter or even into cloud providers, we're taking in metadata from those solutions as well and helping the solution to build address book objects for you automatically. So when we remove these from the network, we actually remove all the dynamic address book entries as well, and we tidy up after ourselves and remove stale address book entries and stale configurations in the network that aren't being used at all. And because it's using IP overlay and it's all using layer 3 routing protocols, we never have to configure VLANs ever again, which is a great thing. And a single API is providing everything from your switching designs, routing, all the way up to stateful firewalling and IPS capabilities as well. So it's fast and it's consistent and it's machine controlled. So how do we actually provide a demonstration of this? We have a requirement inside a university environment in this case to build a cybersecurity lab for a bunch of students that are coming in to run some penetration testing as part of their course curriculum. So we're going to provide each of these students with their own logical router instance, so their own tenancy effectively. And we're going to connect virtual machines to those tenancies. So each of these students will have their own sandpit to play in. They have to be provided with their own IP addresses and subnets, and DHCP has to be configured so the machines can actually function. And then we provide connectivity to some target machines as well. So some devices inside a web tier, an app tier, and a database tier, which would be configured in a lab environment to provide a representative example for these students to actually start attacking. And we have to do all the basic things, the hygiene of a network, so providing addresses, and we have to advertise the routes that we're allocating back into the real core of the network so we can actually route towards them. So we need to be able to reach the virtual machines we're working on, but we also need to be able to provide reachability to the internet to potentially update some of these machines as well, and facilitate the course these guys are running. Once we've deployed this as well, we need to deploy security policy and configure some sort of posture as well, which is representative for the real world, and build that into the network as well. So this is a typical firewall security policy, but because we're running a cyber security lab here as well, we need to have IPS in place to allow the tutor that's running this to actually inspect what is actually taking place and see if he can provide some feedback or even scoring against these students as well about what they're actually doing inside the network. And we need to finally deploy virtual machines as well to actually plumb into these networks to build the entire thing out. So the topology that the tutor came up with was this. So really having a centralized core router, which we're going to call our lab router. This could be the core of the network, and we'll have multiple logical routers connected to this. So in a physical environment, you would allocate everyone a router. They'll plug physical cables into the lab core, and they'll plug that into the core of the network and advertise routes. In this case, we're using BGP to advertise routes into our core platform. BGP is a great protocol to use because it has a lot of controls over the routes that are advertised and the routes that are received as well, which helps us protect the core infrastructure from misconfiguration of subnets as well. And finally, we'll have some security between here as well. So students can't talk to each other to obviously mess with other people's lab environments and sandpits, and the target devices can be scanned and probed against the specific sorts of protocols that would be allowed through that type of tier inside a real application. So this is the topology we're looking at deploying. And through automation, we can logically represent this through, in this case, a YAML plan, a Terraform plan, which is really just a bunch of declarative statements around what we want the network to look like. So this network, for example, here, I've got a resource here, which is a tier 1 router. I'm going to call it student 5 router, but this is a new tenancy that I'm deploying. I'm going to plug it into my core router as well, which I've already got built, which is called peering. And likewise, I need to allocate other networking constructs as well. So what's going to be the IP subnet, which I'm going to attach to that student 5 network, and it's going to be this address here. This is the gateway address, which will be distributed across the entire network infrastructure as a local gateway function directly inside the kernel. And these are the addresses I'm going to use for my DHCP scope as well. And along the way, we can actually start tagging each of these constructs, which we can use to help build security policy as well dynamically for us. We get down to things like looking at firewall policy. So importantly, we're not trying to reinvent the wheel on how we configure things like security policy inside a network. We have a policy, and a firewall policy has a group of rules inside it. Those rules are typically built around things like sources and destinations and services, but we can also integrate this with application awareness through App ID. We also have integration with Active Directory, so we can make it user aware as well. And we can build our IPS rules into here as well if we need to. So this is what this is a declarative representation of what I want my network to look like. And we can kick that off through Terraform through the console. But the first thing we'll do is we'll log into NSX, have a quick look at the current state of our NSX deployment, which is a very vanilla install. I've got one DHCP server running here. I've got one tier 1 gateway. So there is one tenancy in here right now. So it's just a very small deployment for my lab here. A bunch of segments being the networks, so the subnets and all the associated parameters with a network. I can look at my topology as it stands right now, which is very simple. I just have a couple of things here just for my lab operation. And this is actually built in real time based on what's actually been deployed across the network, including all the way down to the virtual machines that I'm interfacing with. And I have no other tenancies configured here apart from these guys, which is just all I need to get this running for my environment here. I can configure other things as well, which we can go into at a later date. And security, so I have a centralized security editor, which is built into the same interface, which is all role-based access control as well. So I can restrict who can get to each of these sections and who can define security policy and who can actually permit and publish that as well into the system. And inventory is looking at tracking the virtual machines on the network, container pods are running, physical servers out there, and things like groups, which my address group objects I use for firewall policy. So it's pretty empty in here right now. So what we're going to do is deploy that Terraform plan. So I'm just going to run here, Terraform apply. I've already run through the planning process before, but Terraform allows me to quickly understand the state of a network and deploy configuration changes to it based on my plan, but also importantly it maintains state with what it believes the network should look like as well. So if I run through a Terraform apply process here as well, it's going to go actually and quickly refresh its understanding of what the network looks like right now. So it's going to go through and see if these services are already configured that I've built inside my Terraform plan, and I'll come back and say, right, this is what I'm going to add to the network. So the plus signs here are denoting, I'm adding things into the state, and let's deploy that. So this will actually now run through the entire Terraform plan and build the logical network that I want, including all the tenancies, all the student routers I want. Attach the networks to them, the subnets, configure the DHCP server, configure the DHCP scope, configure the security policy. If I jump back into NSX-T, you'll see if I hit a refresh on here, then I now have 9 tier 1 gateways. I now have 9 segments. I've got an additional DHCP server. So it's keeping track and maintaining state of all this as well. And it helps us understand, ultimately build up and maintain, keep within the capacity we're allowed to support as well across this network. It's not refreshing, not working. Right, so let's have a look at what we've actually deployed at this stage, right? So we looked at the network overview. Let's look at the topology. So we now see we have these 9 segments here. So let's click on that. We have 9 separate tenancies. Each of these are isolated from each other, and they're obviously all sharing the same underlying tunnel overlay infrastructure. They're connected into the single peering router here, and this has got a BGP peering into my upstream physical router. So I'm going to log into that guy here, and then let's look at the routing table. So the routing table now, through BGP, I've actually received these routes. These are the network segments or the subnets I configured inside my Terraform plan. So part of the entire deployment here is to logically build our network infrastructure, but also allow route redistribution back through BGP into the core of the network, so we actually provide reachability as well into our lab environment for this class. So we'll come back in here and have a look what's going on. So we've got a bunch of tier 1 gateways, some segments associated here as well. We have built security policy. So if we look at our distributed firewall policy, we will see that we've now built, what looks like to most people a very familiar top-down security policy with sources, destination, and services. So we're not reinventing the wheel here. Any security operator can really look at this and understand how this is supposed to function. Now, like a real firewall, we build address books objects, which are used by the firewall policy. They're also used by our IPS policies as well. They're also used by address translation for our load balancing solution as well. So we have these groups here with memberships, and membership criteria for, let's say, this database server here would be, it's very simple. The virtual machine name contains DB server. So anything that matched that would get dropped into this, and we would learn the name of the machine, and we would learn the IP address of that machine, and we would then populate this into this address group object for us. We don't have any virtual machines running right now, so we won't see anything in here. So let's do that now. Let's spin up a couple of virtual machines. So I'm going to go back into Terraform, and I'm going to deploy a bunch of virtual machines. At this stage, I'll also attach those virtual machines to the segments I've created. Those machines will boot up. They'll request an IP address through DHCP, and that will be provided to them by the logical router through the distributed DHCP server we have running in the background, and obviously allocate an IP address to it. And this takes about a minute to run through. So we're actually looking at deploying. We've just deployed a complete network, complete logical construct with all the security in place. We've also advertised those routes through BGP and provided reachability to the outside world to these. So any traffic coming into that network now has to pass through that firewall policy we've also deployed as well. So these machines are going to spin up. They've just been spun up through a bunch of templates inside vCenter here. So we've got some student machines. If you look at the names, I've got DB-server-lab. So that group construct I had before was actually looking at the name of this VM, and this information is pushed down into NSX as well. from vCenter, but could also receive metadata from KVM-based hosts, from Kubernetes clusters, from Amazon Web Services, from Azure, and use that information to help start building dynamic address book objects for us as well. So we're getting there with the creation of these virtual machines. Let's give it just a little bit longer. What we'll see is these machines are booting, they're actually getting IP addresses. And we learn that through VM tools integration as well. So this IP address here, let's jump back onto our switch over here, our router, sorry, and we'll see if we can ping it. We can. So we've provided reachability through BGP, and we're forwarding into the up to the tier 0 router, and that's providing us connectivity to that virtual machine. Right. It's probably finished now. Let's have a look at how it's cool. So we're now deployed all our virtual machine infrastructure. So we jump back onto the NSX-T console, and the first thing we'll check out is our inventory. So before we had all VMs, and the members for those now are all those VMs I've just spun up, and we've actually learnt the IP addresses too. So I haven't had to go in here as an operator and drop in a subnet or an individual host entry into here. The system is actually doing that for us, and if I deploy another VM that matches my all VMs policy, it'll appear in here. Likewise, I've got my database servers that appear here. And if there was another machine that was to match my group definition, which is virtual machine name contains DB server, then that too would also appear in here as well. So it's highly dynamic. It's tracking all the IP addresses. If I re-IP a workload, it'll also follow it as well. So we've got a solution here that's highly dynamic and not specifically bound to any IP addresses. Right, and network operators also have to plan and troubleshoot things in the network as well, so we can do things like NetFlow and port mirroring, and TraceFlow allows us to inject traffic into the network and actually see how things are actually forwarded. So if I look at how does student 1 lab machine get to our web server 2 machine, let's just ask it to do that for us as well. Why is it not working? Okay, I think that's the wrong machine to choose. I think it's still booting up. Let's get back to that in a second. So we've got our inventory here as well. Groups are running. We've got IP addresses being populated into these groups. We've got security policy in place. So we've got a distributed firewall is now operational. We can look at things like IPS as well, and because this is a cybersecurity lab, we have to actually start looking at the type of attacks these students are making against this infrastructure as well as part of the evaluation. So we can come in here and click on an attack. We can see the source and destination. So the client was this address here, the destination target was this one, attack direction, what we're seeing from traffic flow. Look at historical information as well. Let's click on a different one to see what this one tells us. Right, so it automatically links into the virtual machines that are affected for us, so it tells us where we should go and look at it. This can be IDS or IPS, and we can automatically blacklist upstream addresses or quarantine workloads as well if we need to. And we can also obviously link this back into existing CVEs and go and actually read some more information around that attack that's taken place as well. Let's go back and look at my planning and troubleshooting here for a second. Okay. ICMP, virtual machine, yeah, student, database server. Okay, that's better. I think it was still booting before. And I'll look at virtual machine, web server, let's do student 2, that's it, trace that one. So instead of actually going out into the network and logging into individual switches, we actually ask it to inject traffic into the network for us and actually come back and provide the complete path for us. So we're looking at traffic coming from one machine to another. We know exactly which subnet's connected to, where it's going through. It comes back up through the peering gateway and back through here as well. So we can use this to actually help diagnose network issues very quickly for us as well. Right, so that's it as far as the lab has gone. The class is over for these people, and we now need to actually remove these resources from the network. So the great thing about Terraform is we can actually remove everything as well. So I'm going to destroy my workloads first. So bring down all of the VMs that the students were using. They've all logged off and gone home. And it's going to ask me again, do I want to do that? So Terraform is going to run through its plan and remove everything that matches that inside the network. This again takes about a minute or so. Right, we've now torn down those workloads. Let's have a quick look at vCenter. Yep, they've gone. Cool. Now we need to do the same for networking, right? So let's come and have a look at our physical network here as well. So it's going to go through and have a look at its understanding of the state of the network and compare it to what's actually in there. So it's refreshing its understanding of the network configuration. It's then going to say, right, do you want to delete these things? I'll say yes, please, get rid of them. So at this stage, it's now logging into NSX-T. It's removing all the subnets, all the logical routers, all the connectivity between them, the security policy, and all those address book objects we looked at as well, and tidying up after itself. So we've got a network now that's completely back to the way it was before. So it's highly dynamic. I haven't had to log into a single switch or a router to make a change. This is a complete logical overlay for all my networking and security services. So this will take a while to go through. It's actually still busy destroying these networks. Let's have a look and see what's going on inside the interface. So our inventory groups have been removed. Great, so we now no longer have these dynamic address groups here as well. Our security policy, let's look at the distributed firewall, has removed that policy entry, so that entire line has gone. And we can come into our networking section and start looking at our, okay, these are still here. And these are still all disappearing. So these take a while sometimes because it takes a while for it to refresh its understanding of what virtual machines are running on the network and what are attached to a network segment. So let's give it a bit longer. It takes a while to eventually destroy, but it always will once the dependencies from vCenter are being pushed back down into NSX as well. Okay, still here. And we're still waiting for it. It'll get there. It's just making sure that there's nothing still using that network. Alright, here we go. Right, so we'll come back into NSX-T and have a quick look. It's here. Tier 1 gateways have been removed. Let's just refresh that. Cool. And finally that one. So network segments should have been removed as well. The topology will reflect those missing elements. Great. So it took a bit longer to pull it down than I was hoping for a demo, but 2 minutes 50 seconds really to tear that down, but also to wait until nothing was connected to it as well. So it wouldn't actually go away and actually break anything for us as well. It wants to make sure that there's all upstream elements have actually been removed before it actually tears down the network and gets the network into a non-forwarding state, right? So that's it for my automation demo around NSX-T for both security and networking. Francois Prowse is my name, fprowse@vmware.com. If you have any questions, please reach out to me. Happy to help you if I can, and looking forward to hearing from you. Thank you. Bye.